Okay, the example I was promising is right here. I'm sure you're all really excited to see that I didn't forget. Anyway, this is a simple experiment that you could do that would involve collecting gases over water. When you put zinc in a solution of acid, it starts reacting fairly vigorously, and you form, if the acid is hydrochloric acid, you form zinc chloride and you give off hydrogen gas. And the hydrogen gas goes off and it will go through the tube and into the collection chamber where you're collecting the gases. And from there, it displaces some water and you can collect your hydrogen. But again, the problem is that you're collecting gas over water, so the gas you are collecting is actually a mixture of hydrogen and water vapor. So we're collecting hydrogen over water. The total volume collected is 154.4 milliliters of gas collected over water at a barometric pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen was collected? And as an extension of this concept, we might want to go back and find out from that what mass of zinc was reacted, because that would be just a stoichiometry problem. If you can find out how much of this was produced, you should be able to find out how much of that reacted. But we haven't done that before with gases. So that'll be something else we can look at. But we'll do that second. First of all, what we need to do is find out what is the partial pressure of hydrogen. So the partial pressure of hydrogen is just going to be the total pressure minus the partial pressure of water. The total pressure here, according to the problem, was 742 millimeters of mercury. And the partial pressure of water, which you can find in any number of tables, you could probably even Google partial pressure or vapor pressure of water and find a table. It's 23.78 millimeters of mercury at 25 degrees Celsius. And that gives us a partial pressure of the hydrogen alone at 718.22 millimeters of mercury. To use that in the ideal gas law, though, we need that in atmospheres. Okay, so you divide by 760, and we find out that it's 0.945 atmospheres. Then all we need to do is use the ideal gas law. PV equals nRT, rearrange it to find N. N of hydrogen is just going to be the partial pressure of hydrogen times V over RT. Partial pressure of hydrogen is 0.945 atmospheres. The volume is 0.1544 liters. It was 154.4 milliliters. You just divide that by 1,000 to find liters, so it's 0.1544 liters over RT. R is 0.082057 liter atmospheres per mole Kelvin. And the temperature was 25 degrees Celsius, which is 298 Kelvin. You'll begin to remember that after a while because 25 degrees Celsius is such a common temperature to use in problems like this. So 298 K, and that leaves us with 0.005967 moles of hydrogen. The mass of hydrogen is just going to be the number of moles times the molar mass, which is 2 grams per mole. And that's 0.0119 grams of hydrogen. Okay, for the zinc, the moles of zinc would just be converting from the moles of hydrogen. So, and remember, you can't go directly from mass of hydrogen to mass of zinc, but you can go from moles of hydrogen to moles of zinc. So if we produced 0.005967 moles of hydrogen, and the equation tells us that we used 1 mole of zinc for every 1 mole of hydrogen, that would tell us that we must have used 0.005967 moles of zinc, assuming that we had an excess of hydrochloric acid. And mass of zinc is just going to be moles times the molar mass. And the molar mass of zinc is 65.38. And that means 0.390. Let's look at significant figures here. Got 4, we got 4. Yeah, let's go with 4. 0.3901 grams of zinc were used. So you can do stoichiometry with the ideal gas law too. Yay. Okay. In fact, that's what the next section is about, stoichiometry in reactions with gases. So the gas laws provide a new way to do stoichiometry when there are gases in the equation. But actually, you can use gases directly in chemical reactions as long as the conditions don't change. And I know that I've been emphasizing so far that when you're dealing with solids or liquids or solutions, you cannot convert directly from mass of one thing to mass of another, or volume of one thing to volume of another for, say, solutions. But you can do that with gases. And that has to do, again, with the fact that for gases, they all behave the same way with respect to pressure, temperature, volume, and number of moles. So once you've got a volume for a gas, you can go directly from volume of gas A, for instance, to volume of gas B. without going by way of moles. Okay, so an example of that would be synthesis of ammonia, where you have 3 moles of hydrogen gas plus 1 mole of nitrogen gas going to produce 2 moles of NH3 gas. So if you were to conduct this reaction at 500 degrees Celsius and 5 atmospheres pressure, and it really does need high temperature and high pressure in order to go at a reasonable rate of speed. What volume of ammonia would be produced from 0.755 liters of hydrogen and excess nitrogen? So in other words, hydrogen is the limiting reagent. Well, for this, all you have to do is take the volume of hydrogen and look at the stoichiometry. So for whatever volume of hydrogen you put in, you get 2 volumes, say, for instance, 2 liters of NH3 for every 3 liters of H2. And it would have the same ratio with any volume. So you could say 2 gallons of NH3 for every 3 gallons of H2. Whatever units you happen to have for volume over here, you can use those volumes here when you get the stoichiometric ratio. And notice that liters of H2 cancel out. You get liters of NH3 as your unit. And the answer is 0.503 liters of NH3. That's if you want to do it the easy way. If you want to do it the hard way, you can. And just to show you that the easy way works, I'll try it the hard way. So first thing we'd want to do is find out the number of moles of hydrogen that are being produced. So N would be PV over RT. 5 atmospheres for the pressure. 0.755 liters for the volume. Point 0.082057 liter atmospheres over mole kelvins for R. And temperature would be 773 Kelvin. It was 500 Celsius plus 273, that's 773 Kelvin. And that tells us that we produced 0.05951 moles of hydrogen. And using the stoichiometry, we can convert this to moles of ammonia. So 0.05951 moles of hydrogen. And the equation tells us we get 2 moles of NH3 for every 3 moles of H2. And so that should produce 0.039 0.68 moles of NH3. And then you can use the ideal gas law to find the volume of ammonia. V equals nRT over P. So N would be number of moles, 0.03968 moles of nitrogen. R is 0.082057 liter atmospheres over moles Kelvin. And T is temperature, which hasn't changed, so that's still 773 K, all over pressure, which is 5.0 atmospheres. And when you work all of that out, you come up with units of liters of NH3, and the number ends up being, drum roll, 0.503, which is, where did I do it? Oh, right there. So yes, when you're dealing with volume of one gas versus volume of another gas, you can go directly to the stoichiometry and get the right answer. And that's because each mole of any given gas will occupy the same volume at the same temperature and pressure. Another example of using the ideal gas law in stoichiometry would be the reaction where silver oxide decomposes. Two Ag2O goes to 4 silver solid and O2 gas. So if this reaction forms 4.58 liters of oxygen at 745 millimeters mercury at a temperature of 308 K, how many grams of Ag2O were decomposed? Okay, so we've got a pressure that's in the wrong units. So that's 745 millimeters of mercury. And there's 1 atmosphere for every 760 millimeters of mercury. And that is where am I here? 0.9803 for the pressure. Temperature was already in kelvins, so that's good. So we can go on now. So first thing to do would be find number of moles of O2. And that's PV over RT. So that's 0.9803 atmospheres times 4.58 liters over 0.082057 times 308. Let's see, atmospheres will cancel with atmospheres, kelvins cancel with kelvins, liters cancel with liters. We end up with moles on the bottom of the fraction, which is mathematically the same as being on top. So we end up with moles, and that's good because that's what we wanted. That's what N means. And the number is 0.1776 moles of oxygen. Now we can use the stoichiometry now that we have numbers of moles. 0.1776 moles of oxygen. And the equation tells us that we had 2 moles of silver oxide disintegrating for every 1 mole of O2 that's generated. And so that means that we must have disintegrated or decomposed 0.3553 moles of silver oxide. And so the mass of silver oxide will be the number of moles times the molar mass. If you go to the periodic table and add up the masses for 2 silvers and 1 oxygen, you get 232. So 232 grams per mole. And that means we must have decomposed 82.4 grams of silver oxide. Okay. Another shortcut, it deals with molar volume. So at or near standard temperature and pressure, which would be 0 degrees Celsius and 1 atmosphere, we can use 22.4 liters as the volume of 1 mole of any gas. And that actually can make things quite a bit easier also. So for example, how many liters of O2 would be required to form 10.5 grams of H2O at STP, according to this reaction. 2H2 gas plus O2 gas produces 2H2O gas. Well, if we know how much water we need to produce, so we can find out how many moles of water just by taking 10.5 grams of H2O and dividing by its molar mass, which is 18 grams per mole. So grams of H2O cancel. 10.5 divided by 18 is, I'm going to call it 0.5833 moles of H2O. Now that we've got moles of H2O, we can use the stoichiometry in the equation where it says that we have to put in 1 mole of O2 for every 2 moles of H2O. So moles of H2O cancel, and this divided by 2 is 0.2917 moles of O2. And it was what volume, not how many grams of oxygen, but what volume. So now if we know 0.2917 moles of O2, we could put that number into the ideal gas law for 0 degrees Celsius or 273 Kelvin and 1 atmosphere pressure and find the volume that way. But just knowing that at STP, 1 mole of gas occupies 22.4 liters saves us quite a bit of work here. So the there are 22.4 liters for each mole of O2 at STP. So when we multiply this, we get 6.53 liters of O2. And it saved us a bit of work. You can only use 22.4 at STP though, or close to STP. At any other temperature you would have to use, or any other pressure for that matter, you would have to use the ideal gas law. Okay. Hopefully that's fairly clear. The next section is on the kinetic molecular theory of gases, which has to do with the theoretical background of why gases are the way they are. And it gets a little involved, so I think I'm going to end this segment of the lecture a little early, and I'll start in on the kinetic molecular theory in the next segment in a moment.